Hello, good morning SH2 students. Welcome back to my channel. Today, we will still discuss about the nuclear physics, and we are going to continue to discuss about the relations between binding energy, fission reaction and fusion reaction in nuclear physics. I will repeat about the definitions of binding energy. The minimum energy needed to pull a nucleus apart into its separate nucleons, we call it as the binding energy. And yesterday we also have discussed the graph of the binding energy. As you can see here, the binding energy is going up as the number of the nucleons that needs to be bind is increasing, and eventually going down, the binding energy will going down after the iron nucleus. So again, it will goes up from hydrogens until iron nucleus, the binding energy, and then after that, if the number of the nucleons is bigger than the iron nucleus, then the binding energy will eventually going down. We also need to know that the nucleus becomes more stable as binding energy per nucleon increases. So from this graph, we can see that iron nucleus is the most stable nucleus, and then after that, going down, as you can see here, uranium nucleus means not stable. Unstable nucleus will tends to break apart into into a stable nucleus. Same with the hydrogens nucleus. The hydrogen nucleus, if it is not stable because the binding energy here is very small, then it will tends together with other nucleus to form a new stable nucleus. So there are two kinds of reactions here, which is the one that is dismantling or separating the nucleus into smaller number nucleus, and the one that gather and become a bigger nucleus but more stable. Okay, so there are two kinds of reaction, fission and fusion. Nuclear fission and nuclear fusion both release energy because both processes increase the binding energy per nucleon of the particles involved. For example, this hydrogen's nucleus, okay, gather with other hydrogen nucleus, and the result of the nuclear reaction will be a higher state in binding energy. Okay, another example is this one. Okay, we can see this. Fusion reaction. Hydrogen 2 and hydrogen 3, deuterium and tritium, will combine. These two nuclei is not stable. So to make them stable, they need to do fusion reaction. They need together. So become helium-4 and releasing also one neutron. So this reaction will release also energy as much as 14.1 mega electron volt and also plus 3.5 mega electron volt. So this is the fusion reaction gathered. And then after that, another one is fission reaction. As you can see from the graph of this binding energy, a uranium nucleus has low binding energy. So to make it more stable, it needs to be separated into smaller nuclei that have stronger binding energy. For example, a uranium-235 will split into two during fission reaction, become barium and also krypton. Barium-141 and krypton-92, and also 3 neutrons. Of course, energy also will be released here in fission reaction. So that is two kind of nuclear reaction: fusion, gathering, okay, and then fission, splitting. This is the definitions. Nuclear fission is when a massive nucleus splits, forming two smaller fragments. Large nuclei are unstable, as I've mentioned to you, like uranium nucleus, and some will spontaneously split into two smaller nuclei. For example, just now, right? Again, uranium become barium and also krypton. We can induce nuclear fission if we bombard a nucleus with neutrons. And nuclear fusion is when two light nuclei, such as deuterium and tritium just now, this one, become one, join together to create a larger nucleus. This larger nucleus is more stable rather than the light nuclei. Okay, so now it all makes sense. Whatever is the nuclear reaction, either fission or fusion, it will release energy, and both process will increase the binding energy per nucleon. That is for fission and fusion. Yeah. The next thing is randomness and decay. This is actually, we have been discussed previously when we discuss the A-level questions. That is about the nature of radioactive decay. The emissions of radiation is due to radioactivity, happens both spontaneous and also random. Spontaneous means it is not affected by any external factors such as temperature or pressure. So remember, radioactive decay will not be affected by temperature and also pressure. So whatever is the temperature, whatever is how big is the pressure, then it will not affecting the radioactive decay. And also it will happen randomly, means that it is not possible to predict which nucleus in a sample will decay next. Let's say we have 1 mole of uranium, we cannot know which nucleus in that 1 mole of uranium will decay. But we can make mathematical calculations, however, there is a constant probability or chance that a nucleus will decay in any fixed period of time. This is the things that we can calculate. How long that sample will decay until it finish. We can calculate it, but we cannot predict which nucleus will decay next. That is the nature of radioactive decay. Now, so how about the calculations of this radioactive decay? Please wait. Okay, so this one, for example, suppose we observe 1 million nuclei of a particular radioisotope. 1 million nuclei, it's more than 1 mole. After 1 hour, 200,000 of these nuclei have decayed. Then the probability that an individual nucleus will decay in 1 hour is 0.2 or 20% of it, since 20% of the nuclei have decayed in this time. Of course, this is only an approximate value, since we might repeat the experiment and find that only 199,000 decay because of the random nature of decay. The more times we repeat the experiment, the more reliable our answer will be. Now, so we call it as decay constant. Decay constant is the probability that an individual nucleus will decay per unit of time interval. We can calculate it per hour, per second, per minute, or per year. And the unit is in becquerels. We call it becquerels. 1 becquerels is equal to per 1 second. An activity of 1 decay per second is 1 becquerel. So per second means 1 becquerel. Clearly, the activity of a sample depends on the decay constant lambda of the isotope under consideration. The greater the decay constant, the lambda, the greater is the activity of the sample. Means the sample will be fast to be decayed, will be fast to be finished. It is also depends on the number of the undecayed nuclei and present in the sample. For a sample of an undecayed nuclei, how much the nuclei that not yet been decayed, we can calculate A is equal to negative lambda times n, while lambda is the decay constant and n is the number of undecayed nuclei. We can also think of the activity as the number of alpha or beta particles emitted from the source per unit time. Hence, we can also write the activity A as delta n over delta t, where delta n is equal to the number of emissions or decays in a small time interval of delta t. For example, a radioactive source emits beta particles. It has an activity of 2.8 times 10 to the power of 7 becquerels. So that is the decay constant, the lambda. Yeah, this one, the lambda. Estimate the number of beta particles emitted in a time of interval 2 minutes. State one assumption made. Write down the given quantities. Okay, we can write down, and then after that, we can use this formula A equal to delta n over delta t. So they ask you delta n, the number of emissions, how much of beta emissions happens in that time. So delta n will be just times A with delta t. Then you will get 3.4 times 10 to the power of 9 beta negative emissions. Our assumptions is within those 2 minutes of time, the activity will remain constant. If the activity is not remain constant between those 2 minutes, then we cannot calculate the number of beta minus particles emitted. Next sample. A sample consists of 1000 undecayed nuclei of a nuclide whose decay constant is 0.2 per second or 0.2 becquerels. Determine the initial activity of the sample. Estimate the activity of the sample after 1 second. For activity A equal to negative lambda times n, we have A in becquerels 0.2 times 1000, the number of undecayed nuclei. Then we will get 200 becquerels. Okay, And then after 1 second, we might expect 800 nuclei to remain undecayed. The activity of the sample will be then A is equal to 0.2 from this one, okay, times 800. So that the A will be 160 becquerels. In fact, it would be slightly higher than this since the rate of decay decreases with time all the time. Less than 200 nuclei will decay during the first second. Okay, so that is for the example. Now you see the questions number 12, 13, and 14. Number 12, a sample of carbon-15 initially contains 500,000 undecayed nuclei. So that is the N. The decay constant for this isotope of carbon is 0.3 per second. Determine the initial activity of the sample. So for number 12, we can simply use the formula A equal to lambda times N. The N is the number of undecayed nuclei, and then lambda is the decay constant, which is 0.3 per second. So you just need to put in all the numbers here and then find A, the initial activity of the samples in becquerels. Next, for number 13, a small sample of radium gives a received count rate of 20 counts per minute in a detector. It is known that the counter detects only 10% of the decays from the sample, not 100%. So that 20 counts per minute is only 10%. The sample contains 1.5 times 10 to the power of 9 undecayed nuclei. That is the number of N. That means the decay constant of this form of radium. So we need to count first the A, yeah, the initial activity of the sample for 100% of the sample. So we need to count A times number 13, A, yeah, 10 times the count rate of the detector. 10% times 20 counts per minute in the detector. And then after that, we can use the same formula, A equal to lambda times N, but this time we need to find the decay constant, lambda. Yeah, not the initial activity, but the lambda. Okay, so we need to count lambda, then lambda is equal to A over N. A from here just now, and then N is the number of undecayed nucleus. Last number is theory. A radioactive sample is known to emit alpha, beta, and gamma radiation. Suggest 4 reasons why the count rate measured by Geiger counter. This Geiger counter is the counter of radioactivity decay. Yeah, so this Geiger counter can count, yeah, how much nuclei has been decayed at a time. Place next to this sample would be lower than the activity of the sample. Okay. Now, some of the reasons can be this one. Gamma rays is weakly ionizing for the gamma rays only, yes. So it is sometimes not always detected. And then can be also the Geiger counter is not efficient. So the count rate will be lower than the activity of the sample itself. You can find other 2 reasons from internet. Okay, that's all for today. So for today, you need to do the questions on our textbook, page 499, number 12, 13, and 14. Thank you for your attention. See you again. Bye-bye.